37 or 25 apples and 3750 oranges. Once we establish the indifference curve, we're really interested in the slope. Right? So this shows me this amount of oranges is how much I would give up for, say, 1 apple. So here I would give up, say it's 10 oranges. It's not in Eric's case, but leave it. All right? Here I have a lot of oranges, so I'll give up 10 oranges for 1 apple. Over here, I don't have very many oranges, so for 1 apple, I would give up very few oranges. Right? So down here, I might give up 1/5 of an orange to gain 1 apple. Okay? The slope is the exchange of y for x along an indifference function. Every point above it is preferred to any point on the indifference function. Any point below it is preferred to any indifference function referred to. So that sketches out. This is like an isobar of the altitude line. Now it turns out, now this is going to be a question that gets at what you're thinking. If a person, forget the way I drew this, I'm going to draw 2 types. I'm going to draw this one, and now I'm going to draw this one. 2 different, this is for 2 different people, everybody. 2 different people. Oh, first of all, let's talk about this. Supposing this is the same person, could the same person have intersecting indifference functions? Could that happen? Could a person have indifference functions? Could indifference functions for a person, and this is the indifference map of one person. You can't even compare the indifference map of different people. Could this person have intersecting indifference functions? Let's figure it out here. I'm going to call this point B. I'm going to call this here point A, and I'm going to call this right here point C. Now, you're going to prove to me, using the axioms by contradiction, you're going to say that if the indifference curves can intersect, there will be a contradiction in the relationship between A, B, and C. All right? Okay, first of all, let's just look at A and C. Which one is preferred? A and C. Just look at this. Forget everything else. Which one is preferred? More is preferred to less. Now let's look at the relationship between A and B and C. Therefore, by that, given the relationship between A and B, and the relationship between B and C, what is the relationship between A and C? How, sorry? No, you're looking this way, that's true. What's the relationship between A and B? They're on the same indifference function. If they're on the same indifference function, what is the relationship between A and B? They're indifferent, right? They're indifferent, they're on the same indifference function. What's the relationship between B and C if they're on the same indifference function? They're indifferent. What is the relationship between A and B and C if A is indifferent to B and B is indifferent to C? By transitivity, they're indifferent, right? If they intersect, transitivity would imply that A is indifferent to C. A can't possibly be indifferent to C, therefore that's a contradiction. Indifference functions can never intersect. Never. All right. Okay then. Now let's suppose I'm comparing 2 different individuals, and for that reason, I'm going to have a different color here, and we'll make this color green like this. Okay. These are 2 individuals, 2 different individuals. Now look closely at this and tell me which of the individuals prefers oranges more, the green individual or the red individual? Which one of them prefers oranges more? Yeah. Red. Huh?
Red.
And how did you get red?
Because they don't require as much compensation in oranges.
Yeah, perfect. And that's a very good answer, a very sophisticated answer at this level of analysis, and I certainly didn't have when I first looked at it. Because what we first notice is we want to see whether the person prefers oranges or apples. So most people see, look, there's more oranges up at the top top there, see that green seems to have more oranges, right? Whereas the other one, the red, seems to have more apples over the far right. So your eye is attracted to that, and you say, the red, because there's so many more apples over here. Look how many apples there are over here. And there's not as many oranges over there. But that's not what you look at. You look at the slope, right? And you see, as he pointed out, so far as we're looking here, well, actually, I can't remember what I said. This one would give up this amount of oranges to gain this amount of apples. But notice, this one would give up, to gain the same amount of apples, would give up many more oranges to gain the same amount of apples. This person prefers oranges, notice it? Because the slope is steeper. So we can therefore the indifference functions, we're in this class we're not going to be too worried about this, but I expect you to understand that. But essentially we want to say the indifference map, the shapes can be flatter or steeper depending whether the person prefers y or x. And also, we can also shift them. We're going to see. It turns out there's an infinite amount of these things. So in fact, if I did this, there's one right here at 51 and 51. There's one right here at 52 and 52. There's another one right here. There's another one right here. Another one. And the whole space has indifference functions. And so that basically now, if you said to me, like, I didn't really know before, but for example, did I prefer this point here, right there, to say this point right here? Which one do I prefer? Do I prefer this point or this point? Now imagine the indifference curves aren't there, you just got 2 points in space. You'd have no idea. Which one do I prefer? This one or this one? This is A. Which do I prefer? A or B? Which one do I prefer? A or B? No, you're looking at the indifference map. Which one do I prefer? A. Who says A? Go ahead, tell me why.
Because if you draw an indifference curve, the indifference curve that used to A is higher than the one that used to B.
Yeah, but also even with the ones here in our map, you could say A is preferred to every point on this indifference function, right? And every point on this indifference function is preferred to B, so you can do it just like that, right? So the indifference map sketches it out. On the other hand, if it was even flatter, maybe B would prefer to A. If it was steeper, maybe there would be a different thing. So the indifference map is an infinite number of indifference functions. They lay out that map. It's like an altitude. And it allows us to look at any combination of goods and tell which one is preferred to the other. And that's all we want to do. Okay? Now, so far as the sophistication is concerned, this isn't great for us here. But I'll just point this out. The indifference functions can have different, they're flat or steeper, they can have different slopes. But also, in space, they can radiate out differently. So for example, here, I have them kind of radiating out kind of in this direction. When that happens, it's kind of an income effect. If they go straight up, there's no income effect. I'll talk about that later. Or they could literally go right out sideways, right? So the one thing they can't do is intersect. So it turns out, in more sophisticated economics, we examine how that map is and talk more about consumer preferences. They do some of that, but not a lot of it. Okay? So, this is where we're at. Now then, I'm going to just draw one here. I'm going to draw an indifference function like this for some individual. It looks like this. How do you like it? Does it look like an indifference function? function to you according to our axioms? This one right here? Something is wrong with it. What is it? Yeah. Yeah, it can't curve up. Why is that? Because, yeah, go ahead.
Because we're trying to say that they're, I think, on the right graph, the same as the point to the left, which kind of means that, well, there's one on the right, right? So we compare.
Yeah, exactly.
It's on the same.
You could look at the same line and get some kind of contradiction, but in particular, this must be referred to this, so it can't happen. Ready? Okay, now, the indifference concept is a kind of, it's very abstract. But now I'm going to show you a diagram you guys are going to draw along with me. You have to completely absorb this. But I'm going to put the budget line and the different functions together, and we're going to derive demand. And you must learn all of it whenever I do a diagram. Everything is sequential, logic. This causes this, causes this, causes this, causes this. And if you're tempted to memorize, yes, if you have to go to the final exam and you don't have a clue by all means to memorize, do the best you can. But at all other times, try to understand this is the process at a university. If you can't do this, you cannot really do anything in university other than get through med school. That's it. Everything else requires thought, right? But memorizing, no. Okay, so here we go. Now, watch carefully. I want you to draw such a diagram as we have here, like this. On the vertical axis, the quantity of y. On the horizontal axis, the quantity of x, which could be any two commodities. Now this might, the reason I'm jumping to this, I'm not really jumping, it's a natural progression, but hopefully you'll see where we're going, okay? And then down here, I want a second diagram, like this, right here. And this diagram represents the price of x, notice, not the quantity of y, the price of x, and the quantity of x over here. Right? Okay? Good. Now, attention. What we're going to do is we're going to derive a demand function. Now, everybody in this room can define a demand function. What are the three parts of the demand function that are important to us? Name one. Come. Yes. Huh? No. Fundamentally, definition. That's an observational point. Demand function is. Yeah, go ahead. Notice the pieces. The quantity demanded at each price, every price, ceteris paribus. Now, if we get this, in other words, if we have a price and we find out the quantity demanded in response to that price, and all the ceteris paribus conditions are satisfied, we have a quantity demand in response to that price. So we need to satisfy the ceteris paribus conditions, which are income is fixed. The price of all other goods is fixed. Preferences are fixed. These are the main ones. Okay? So, here's what we're going to do. I'm going to define the quantity of y. I'm going to define y basically as all other goods. You'll tell me why I did that in a minute. Then I'm going to assume, and when you do a demand function, I want you to do this. To remember that y represents all other goods. And then over here we're going to assume fixed the price of y, income, and preferences. Why do I do that in the first place? Why do I assume these things are fixed? Yeah, Erica. Yeah. Now the ceteris paribus conditions are satisfied. Income is fixed, preferences are fixed. Why did I assume Y was all other goods? Why did I assume Y was all other goods? Yeah, so I don't have to worry about complements and substitutes, and by that one stroke, I'm able to assume if the price of Y is fixed, the price of everything is fixed. Okay? So now we have the conditions. Now your next thing, think about this. We begin at this moment of time with M given, income is given, the price of Y is given, preferences are given. Now I claim that we have at least 1 point on the budget line. Which one is it? Before we even begin. Which point do we have on the budget line? Because we might not remember the whole budget line business. Do we know one combination of X and Y that a person could buy? Do we know one? We do, Eric. If we bought, at the moment, if we bought nothing but Y, we can say that. So watch the logic. With this information now, we can say, we can pick this point before we even begin. This point right here, we can pick, because it is, this is how the budget line is, it is M divided by the price of Y. Okay, read? So we have that. Now watch. So now we're ready to begin. I'm going to pick a price of X. And because of the ceteris paribus conditions, and because this preference, this could be a person with flat or steep and different functions, strong preference for Y, strong preference for X, strong income effect, don't worry about that for the moment. All this stuff, doesn't matter to us. When I pick X right here, this is the price of X right here. In particular, this is the price of X all the way along. This is the price of X. Now, having picked X, what point, the price of X, what point do I know on the indifference function? Do I know any other points in the indifference function? It's trying to think. Yes, go ahead.
M divided by PX.
Yeah, M divided by PX. So as soon as you do that, no crinkling. Stop and wait. Okay? Don't even think about it. I'm going to enlist this class to stone you if you crinkle. I'll eat it by firing my mouse at you. And everybody else can throw whatever else they want. PX0, okay? That's the one rule, don't forget. PX0. Because it's not just PX, because we're going to have different things. This is PX0. Now, by the way, do we have any other points in the budget line? Biggest thing. It turns out we have all the other points in the budget line. If you know the price of X, the price of Y, and your income, you know all the combinations of X and Y. So once you pick the price of X, you have the budget line. Like this. Right? Ready? Now then, we have to figure out that limits. We can't buy these goods, and we can buy these goods. So we have to figure out what is the combination of goods that this person prefers more than any other. It turns out, and when you guys draw it, when I ask you this to draw it, and I don't give you any more instructions, you just draw the indifference function any way you want. Say like this. This would be typical in this space. It can slope up, and it must never intersect another one. Other than that, that's all that matters. Right? Now, could this person buy any combination on this indifference function? Yes or no? No, they can't. They can only buy these combinations. What about any combination here? Could they buy any of those? No, they cannot. Now, think about this. What about if they could buy some combinations like here? This indifference function. Given that they can buy some of those combinations, remember they're indifferent to this one, and this one, and this one, and this one, this one. Given their budget, which is the combination or combinations that they would prefer most? Given this information. Okay, and this is a good answer. Hang on, Kyle, I'll get you next. She said the intersections. Now I like the answer, but it'll be wrong just in a second. But she's recognizing the person spends all their budget, which is what we want them to do, and they can't buy this But these, they're indifferent to. All these points are indifferent to. So if we're going to have them spend all their budget, which we want them to do, these 2 points spend all their budget, and they're equal to all the other points, so that would satisfy. But we want to be more sophisticated in the spending of the budget. What do you think, Kyle? Yeah. So once we recognize that those are 2 good choices, why isn't this a better choice right here? Right? Any choice in here has an equal preference. You know, they're different between this and this bundle, but what's the advantage of this bundle right here? They have unspent income, right? So they would buy, say, this bundle, but then they have income to spend, so they move up a bit like this. But then they also have income to spend. It turns out if you take this to its logical conclusion, which is right here, they will move to the point, they maximize their preference. You know, they pick the combination that is best for themselves, given their budget, at the tangency of the highest indifference function in the budget line. So this gives us this result right here. This is the best possible combination of X and Y this person can buy. This is X0. Given that budget line, X0, right? Now notice, if this indifference curve was one tiny bit higher, they couldn't buy. If it was any lower, they could improve their situation. So this is the best combination they can buy. Now notice, by the way, this gives us a very important result, which is consumer equilibrium, which means maximum preference. They pick the best combination. The combination they prefer the most implies tangency of budget line and indifference function, right? Which, by the way, implies this. Now watch. It implies that the trade, remember D stands for exchange, or change. The change in the quantity of Y, quantity X, for the market is equal to the exchange of the quantity of Y and quantity X for the individual. And that's considered to be the great result of consumer equilibrium. That consumer equilibrium, when the consumer can do no better for themselves, the consumer is exchanging X for Y, or Y for X at exactly the same ratio as the market ratio. Oh, by the way, what determines the market ratio? Would anyone know from last day? Well, it turns out you get this formula. The market ratio, remember this now, but again, we didn't want you guys to study it, but now I want you for next day. This implies the negative of Px over Py. That determines the market ratio of exchange of X and Y, or Y and X, is equal to the marginal rate of substitution. This is this huge formula for supposedly for consumer equilibrium. And we'll talk about that next day. One final point. Given that equilibrium, that X is a consequence of the price of X, that. That X is a consequence. So it turns out, right here, this point right here is our first point on our demand function. We derive 1 point. Right? Now, a lot there to absorb. Please think about it before Wednesday. But those of you who did not feel comfortable with this exam, go to see the TA tomorrow and Monday before it bites you, which it sure will down the road. Right? Good. We'll see you on Wednesday.